Welcome back, Physics 30. This is the new section FI2, also involving force fields. FI1 dealt with gravity fields, and FI2 looks at investigating electric and magnetic fields and their interactions with matter. So here we'll look at 8 different things here. Coulomb's law for 2.1, electric field lines, magnets and magnetic fields, electric currents producing magnetic fields, the force on an electric current in a magnetic field, force and electric charge moving in an electric field, and also some applications involving these types of fields. So first of all, we'll look at 2.1, Coulomb's law. We'll apply Coulomb's law to determine the magnitude of the electric force between point charges separated by a distance and state whether it's attraction or repulsion. So in earlier grades, you've seen that an electric charge exerts a force of attraction or repulsion on other electric charges. What factors affect the size of this force? So for example, you learned that like charges, such as 2 negatives close to each other, repel. 2 positive charges beside each other, repel. And if I have opposite charges, such as a plus and a minus, then they attract. So those are the forces we're talking about here. To find an answer, the French physicist Charles Coulomb investigated electric forces in the 1780s using a torsion balance seen below right. And you can see that it's very similar to the Cavendish experiment if you look at, just to take a quick look at this schematic here. Precise instruments for the measurement of electric charges were not available in Coulomb's time. Nonetheless, Coulomb was able to prepare small spheres with different magnitudes of charge in which the ratio of the charges was known. So, for example, does one sphere have double the charges or triple the charges of something else? Although he had some difficulty with induced charges, Coulomb was able to argue that electric force one tiny charged object exerts on a second tiny charged object is directly related to the charge on them. So the more charged, the greater the force. So that is, the charge on either one of the objects is doubled, the force is doubled. If the charge on both of the objects is doubled, that's 2 times 2, 4 times the original value. This was the case when the distance between the 2 charges remained the same. If the distance between them was allowed to increase, he found that it was decreased with the square of the distance. And this is very familiar because it's the same relationship as we saw with gravitational force. Thus, Coulomb concluded the magnitude of the force F that one small charged object exerts in a second is proportional to the product of the charges and inversely proportional to the square of the distance between them. So originally, force is related to Q1, Q2 over R squared. So if, let's say, these become doubled, times 2 times 2, so that's 4 times as great, if I leave the radius the same side. If I leave these charges as times 1, don't change them, but if I double the radius, we can see here, this is now 1 over 4, which is 1/4 times bigger. So if you increase the distance, you decrease the force by 1/4. So inverse squared for radius and directly proportional to Q. If I made one of these 3 times, it'd be 2 times 3, which is 6. Now in changing that into an equation, we introduce a proportionality constant, which is called Coulomb's constant. So this equation gives the magnitude of electric force that exists between 2 charges. So charge 1, charge 2 separated a distance. I can use that relationship on the previous page. The direction of the force is always along the line joining the 2 charges. So the force is along that line. The 2 charges have the same sign. So if this is positive and positive or negative and negative, they of course repel each other, because you know from earlier grades that like charges repel, whether they're 2 positives or 2 negatives. If the 2 charges have opposite signs, so for example, one is positive, one is negative, opposites attract. In the figure below right, notice that the force on one charge exerts in the second is equal and opposite. So if you look over here, Newton's third law, right? If there's a force exerted on 1 by 2, it's equal and opposite to the force exerted by 2 on 1. So equal and opposite. So you can see here, positive, positive, repel. Negative, negative, repel. Positive, negative, attracts. The force that is applied to 2 exerted by 1 is equal to the force exerted on 1 by 2. The SI unit for charge is the Coulomb, shortened down to big C. The precise definition of the Coulomb today is in terms of electric current and magnetic field, and will be discussed later. In SI units, the constant K is this: 9 times 10 to the 9 Newton and meter squared divided by Coulomb squared. Because Q is in coulombs. If you look down here, Q, the charges are in coulombs, meter squared, so you want the opposite here. So we end up with units of force, which is newtons. So if the charges of 1 coulomb for each of these charges separated by a distance of 1 meter, we get a force of 9 times 10 to the 9 newtons. This would be an enormous force equal to the weight of almost 1,000,000 tons. We rarely encounter charges this large in terms of coulombs. Charges produced by rubbing ordinary objects, what you may have done in grade 9 science, such as a comb or plastic ruler, are typically microcoulombs. And 1 microcoulomb is 1 times 10 to the minus 6 coulombs. So we're talking about a really small amount. Objects that carry a positive charge have a deficit of electrons, whereas negatively charges have an excess. So recall, ladies and gentlemen, that if you have an object, to make it negatively charged, so it's neutral to start off with, I'll just write a positive and negative. If I want it to be negative, I add electrons, and then it becomes negatively charged. Okay? Negatively charged. If I want it to become positively charged, I need to remove electrons, and then it becomes positive. So you don't add protons or take them away because they're tied up in the nucleus. Without a nuclear reaction, we can't access them. So in terms of making something positively charged, you have to remove the electrons, and then that leaves positive charges behind. Whereas if you want it to be negative, you add an electron. So it's always in terms of electrons, whether you have excess electrons added on, or you have a deficit of electrons because you remove them. The charge on 1 electron has been determined to have a magnitude of a really small amount of coulombs, 1.602 times 10 to the minus 19 coulombs. So that is what 1 electron or 1 proton would be in terms of coulombs, how many charges. That's the smallest charge observed by nature, so it must be the charge of a single elementary charge, whether that's proton or electron. The symbol E is often given or used to describe that, and it is referred to as an elementary charge. So we can write down elementary charge is either 1 proton or 1 electron. So I use the symbol P plus for proton, E minus for electron. Neutron, we can talk about that for no charge. But 1 elementary charge, whether it's an electron or proton, has that amount. So if you look at the next page, 1 elementary charge, 1 proton, or 1 electron is equal to 1.602 times 10 minus 19 coulombs. Or if we divide each of these sides by 1.602 to represent, okay, well, what's 1 coulomb then? That's how many elementary charges. So it all depends what you want to define. Do you want to define this in terms of what 1 elementary charge is, or do you want to define in terms of what 1 coulomb is? So you can see it takes a lot of electrons or a lot of protons to equal 1 coulomb. 6.242 times 10 to the 18. That's a huge amount. Note that E is defined as a positive number, so that the charge on an electron is going to be, well, the opposite, negative E. The charge on a proton, on the other hand, is positive E. Since an object cannot gain or lose a fraction of an electron, the net charge on any object must be an integral multiple of this, because you can't get less than this number, because that's what 1 electron is. So we say that electric charge is said to be quantized. So it exists in certain whole number amounts, whether the smallest being 1e or getting bigger, 2e, 3e, a million e, etc. Because e is so small, however, we normally do not notice this discreteness in macroscopic charges, which seem continuous. Coulomb's law looks a lot, of course, like this. We talked about that. And they both have the inverse squared law. Both have a proportionality to a property of each object, mass for gravity, electric charge for electricity, and they both act over a distance. i.e. they don't need to be touching. The major difference between the two laws is that gravity is always attractive. Yes, that's an interesting point to note. With gravity, there's always attraction. We haven't discovered yet repulsion in terms of gravity, but in terms of an electric charge, of course, there's repulsion, attraction. So gravity versus electric force versus gravitational force. So electric force can either be positive or negative due to attraction or repulsive. Electric charges comes in two types, positive and negative, whereas gravity is only positive, is what we described. Coulomb's law applies to objects whose size is much smaller than the distance between them. Ideally, it is precise for point charges. So remember with gravity, we had, when we're talking about Earth and an object, we had to take the radius of the Earth into account. But with electric charges, they're so small that we don't have to worry about that. We just simply treat them as a single point. So R just represents the difference, the distance between them, because they're so small. Whereas gravity, we often did have to take radii into account. If the two objects are spheres and the charge is known, so it's distributed equally around it, so we just assume that R value is from the center. Coulomb's law describes the force between two charges when they are at rest. That's an interesting thing to note too. In this section, we discuss charges at rest. So if they're a certain distance apart, what's the force at that moment? Because of course they'll attract each other, repulse each other, etc. The study, this is referred to as electrostatics, and Coulomb's law gives the electrostatic force. Okay, I think we'll stop the video there and we'll come back with part 2.